here we go. So this is section 5.1, area and distances. Remember, this is within chapter 5, which is all about integrals. And integrals is basically like finding area underneath a curve. Okay, finding area underneath the curve. We haven't really learned that yet, but that's really what it is. We get to it in section 5 too. And we kind of get there by using this rectangular approximation method. Rectangular approximation method. There's a left side rectangular approximation, and then there's a right side rectangular approximation, meaning that if you put a point on if you make the rectangle the top left piece that's on the function, then that's a left side approximation. If you make it on the right side, then that's the right side approximation. You know, we looked at it in terms of x squared. This was an underestimation if it was on the left side, and an overestimation if it was on the right side. Okay, because all of the extra area was included, so we knew that it was an overestimation. And then we discussed the midpoint approximation, the middle approximation, where it was going directly in between, because then we have some overestimation, some underestimation. Okay. Now, we did this whole problem yesterday that I've already made a note for myself to not put in the notes for next year. I thought it was really cool, but I don't think you guys thought it was cool as I did.
What told you that?
I know. But we said the limit of that sum actually equals 1/3. We are going to find that what we're going to be looking at for integrals are the limit of sums. The limit of sums. As I increase the amount of rectangles I find, it's going to get closer and closer and closer to the actual sum, the actual area underneath that curve. If I make that area, if I make those amount of rectangles go to infinity, the amount of extra area, or not enough area, you know, the amount of extra area, if I'm going on the right side, the amount of extra area will get smaller and smaller and smaller and smaller. Okay? And what I'm doing here is I'm finding the sum of all of those rectangles. I'm finding the area of each one of those rectangles. So what I have is the limit of a sum. The limit of a sum. That's what we're going to be looking at here. Okay. I know I showed this diagram yesterday where, you know, it's that idea of making that n, that the number of intervals that I have, bigger and bigger and bigger and bigger. So until it's, you know, until the extra area is kind of negligible, until it's just kind of gone away, right? And what we can do is we can kind of find an upper region and an upper boundary and a lower boundary for the area. We know it's somewhere between 0.3434 and 0.32. We proved yesterday that it was actually 1/3. All right, now let's apply the idea of examples 1 and 2 to more general region of some function. Like, so what if it's not just x squared? What if it's something funkier than that? What if it's something that, you know, waves, maybe it's sine, or maybe it's a different polynomial that will go up and down kind of erratically, okay? What we're going to do is we're going to apply, and let's say that it doesn't start from the y-axis. Let's say that it starts from an interval a to b, right? So say I'm given some curve, whatever it may be, along the interval a to b. Along the interval a to b. What I'm going to do is I'm going to cut it up into n amount of strips. Okay? I'm going to cut it up into n amount of rectangles. So what I have is I have those rectangles, and I'm going to add the area of those rectangles up. Okay? The width of each rectangle, the width of each area, the width of each rectangle is going to be the same. I hope you noticed yesterday that when I was calculating the area there, it was always, you know, 1/4 times the height. 1/4 times the height. Because that's the amount of intervals I broke it up into, that's what the base came out to be each time. So what if I change up that base, what is it always going to be? Well, it's going to be this distance divided by how many times I take my interval. How many strips of area I take. Well, that's going to be n. Right? The amount of strips that I take, the amount of rectangles that I take is going to be n. So to figure out what each little piece there is at the bottom, to figure out what this is, what this is, what this is, what this is, all of those distances in there are going to be the same. And it's always going to be, I'm thinking about taking I have n amount of strips. I want to figure out what the distance is, and I'm going to divide it up all evenly n times. So to do that, it's b minus a, because that's this distance in here, right? This is the full length is b, subtract away a. That distance in here is b minus a, divided by how many intervals I take. And in this case, I'm taking an arbitrary amount. I'm taking n. That's going to be an important formula there. Change in x, delta x, is going to be b minus a divided by n. That's the interval. The width of each interval is going to be b minus a over n. And it's all cut up into these subintervals. x0 to x1, x1 to x2, x2 to x3, xn minus 1 to xn. Now, each value, x1 is going to be a plus the change in x. My starting value plus my distance. My starting value plus my distance. Because I'm making this not start at my y-axis. I'm making this start at a units away from the y-axis. So to figure out what this full length is going to be, like say I start here, I want to find the value here, the y value. I'm not going to plug in just the interval. I'm not going to plug in just a to x1. Like before I was plugging in like 1/4, and then 2/4, and 3/4, and 4/4, right? I plugged in just the 1/4 each time. What I want to do is I want to figure out that full length, because that's going to give me the true y coordinate. That's going to give me the value here that I want. So technically, x1 is really equal to a plus my interval, right? A plus my interval. And then x2 is going to be a plus 2 of my intervals. That's going to give me my full x2. And then x3 is going to be a plus 3 of my intervals. And then x4 is going to be a plus 4 of my intervals, right? And then it can go all the way up to xn, which is a plus n of my intervals, okay? So each value there, each x value that I choose is going to be your starting value plus however many times you're taking your strip, whatever strip you're on, times the interval that you have. Okay? We didn't really have to worry about that when we started with our very first problem, because we started with the y-axis. And we didn't have to worry about that because I started at 0. If I wanted only distance, like from 1/2 to 1, well, then that would be a different story. I would have to do that whole process where I take my starting value plus my interval, a plus my interval. So say I wanted to find the area underneath the curve from 1 to 4. Well, then I would need to take strips starting at 1 plus my interval, and then 1 plus 2 times my interval, and then 1 plus 3 times my interval, and then 1 plus 4 times my interval, depending upon how many strips I want to break it up into. Okay? Now, what was at the bottom of this? Didn't want to say anything about that. Oh yeah, so the final sum, right? What is the final sum then? Well, it's the interval times the height, right? It's always the base times the height of that rectangle. What is the height of that rectangle? Well, it's the x value plugged into the function, right? For x squared, it was, that change squared, right? Because it's just x squared. Whatever function it may be, this is an arbitrary function f. I'm gonna do the interval times whatever x1 plugged into the function it ends up being, right? So if I change up the function, it's going to change up what the f of that number is. So say I wasn't doing x squared, but maybe the square root of x. Well, then I've got to take your first term, your x1, which is a plus delta x, and plug it into the square root of x. And then I'm going to take the interval times x2, which is a plus 2 delta x, plugged into the function, whatever that number turned out to be. And then I'm going to take f of x3, which is a plus 3 delta x, plugged into the function, times the interval. See, what I'm doing here is I'm taking each rectangle, right? That is the area of each rectangle. The delta x, the change in x, the space of the interval, the width of the little rectangle, times the height of the rectangle. And the height of the rectangle is always dependent upon what the function is. I've got to plug in that value into the function. What value am I plugging in? Well, it depends on which strip you're on. To figure out what the value of that x value is, you got to take your a value plus however many intervals you're on. So a plus 1 delta x, a plus 2 delta x, a plus 3 delta x. Because that's how many intervals you're going to add on to figure out what your full x coordinate is. Figure 12 shows this approximation for 2, 4, 8, and 12. Notice that this approximation appears to become better and better as the number of strips increases. Obviously, if I increase the amount of strips, it's going to get closer and closer and closer and closer to the actual sum, right? See, do I know, based on the look of this graph, do I know what's going to be an underestimation versus an overestimation? No. See, that's where we were talking about yesterday, is right side always going to be an over and left side always going to be an under? No. That's always dependent upon the type of function. I'm not even given this equation. I don't even know what it is. Just some funky curve going from A to B. But as I increase the amount of strips that I take, as I increase the amount of rectangles that I take, it's going to get closer and closer and closer to the actual sum. So what I want to do is take that number of strips that I take and send it to infinity. I want to make the number of intervals that I break it up into go to infinity, because if I do that, then the total area that I have is going to get closer and closer and closer to the actual area. So we have our definition down below. The area of any region that lies under the graph of a continuous function is the limit of the sum. It's the limit of the sum of the areas of the approximating rectangles. So what is that equal to? Well, A is equal to the limit as n goes to infinity. I want to take that number of strips that I'm taking and send it to infinity of the sum. Okay, what is the sum? The sum is interval times the y value. 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 And what is the y value? The y value is a plus delta n, or delta x. A plus delta x. The original amount that I started with, hopefully you're at your y-axis, so you can start with 0. But your original amount that you started with, plus how many intervals you have. See, we didn't even know that whole delta, that f of x1, x2 thing, right? Because we had concrete numbers. We were looking at from 0 to 1. So if I picked 4 intervals, we were picking 1/4, 2/4, 3/4, 4/4. What were we really doing there? We were saying 1 delta n, 2 delta n, 3 delta n, 4 delta n. Because we were breaking it up from 0 to 1. 1 minus 0 over 4, we were breaking up into 4. A minus b over 4, 1 minus 0 over 4 gave us 1/4. That's how we knew we were going to be taking strips of length 1/4. And then multiplying it by the y value of the coordinate. Okay. A little bit in sigma notation. It's going to kind of take a pause and remind ourselves, maybe you didn't learn this, maybe this is stuff like you really need to dust off the cobwebs a little bit. For sigma notation is that funky looking E. That's your sigma. That represents the sum of, right? The sum of, okay? The sum of, whatever down below, that's your starting value, okay? This tells you where you're going to start. So like this sum, it tells you, okay, I'm going to start with M. This sum, it tells you I'm going to start with 1. That's where it's going to start. The starting value is below. So if you need to make notes to yourself, do so, because we're going to be using sums a lot. The starting value is below the sigma. The ending value is above the sigma. Starting value is down below. Final value is up above. And this is f of xi, which is basically f of any number that you use. F of x1, f of x2, f of x3, f of x4, all the way to n. That's the I term times delta n. So that's really going to equal f of x1 times delta x, f of x2 times delta x, all the way up to f of xn times delta x. Those two are equivalent statements. That sum notation, that summation notation, that sigma notation represents that sum that we were just working with. So the area underneath the curve is the limit of that sum. It's the limit of that sum. It's the, as n goes to infinity, from I is equal to 1 to n of f of x times delta x. Okay? From f of x times delta x. This is just another way to write it over here. The limit as n goes to infinity of I is equal to 1 times to n of f of xi minus 1 delta x. That's just going from 1 underneath it. Okay? It gives you the same sum. Because again, n is going to infinity. So it doesn't matter where it comes from, those two. Again, this is kind of a good little, snapshot of everything you need to know about summation notation. Okay. So if you need to write that in, go ahead and do so. All right, let's take a look here. Let A be the area of the region that lies under the graph of f of x is equal to e to the negative x between 0 and 2. I got to get my, I should have my notes down. Okay, so let A be the area of the region that lies underneath the curve of f of x is equal to e to the negative x between 0 and 2. Estimate right endpoints, find an expression for A as a limit. Do not evaluate the limit. All right, now if I'm thinking about this as a curve, like if I want to draw the diagram out real quick, I can see that e to the negative x, that's e to the x, which is an exponential reflected across the y-axis, right? If I put a negative up in the exponent, it's a reflection across the y-axis. So if I want to go from 0 to 2, how many? No, I don't say how many I cut it up into, do I? So from 0 to 2, here's 1/2. There we go. What would it be at 0? E to the 0 would be 1, right? Oh, no. Yeah, e to the 0 would be 1. Okay. So we're starting here and ending somewhere here. Okay. The goal here is to find this area. That's the goal. Find the area of that piece. Okay, so let's figure out my change in x, my delta x. Remember, delta x is equal to b minus a over n. B minus a over n. Well, this is going from 0 to 2. So b minus a is 2 minus 0 over n is 2 over n. And we don't know n. Right now, we're not setting n. We're not saying only 4 rectangles. We're not saying 6 rectangles. We're saying n rectangles. So therefore, we have 2 over n. Because the final sum, like thinking back to this here, the final sum is going to be, where do I have it? The final sum is going to be f of xi times delta x. So we need our delta x in there. All right. Now, each x value is going to be, well, remember the x value, xi, whatever you want to call it, each x value is going to be the starting value plus delta x. Actually, times the I term, right? So if I is 1, if it's my first term, it's going to be delta x times 1. If it's my second term, it's going to be delta x times 2. If it's my third term, it's going to be delta x times 3. The nice thing about this is I'm starting from 0, aren't I? So xi is really equivalent to 0 plus delta x times I. Or in other words, delta x is 2 over n. So it's 2 over n times I. And what I is, again, I is just the term number that you're trying to find. I is the term number that you're trying to find. So like if I'm thinking about it, x1 would be what? 2 over n times 1, right? So x1 would be 2 over n. What would x2 be? Well, that would be 2 over n times 2. So 4 over n. x3, that'd be 2 over n times 3, or 6 over n. You follow me there? That's what I'm getting at when I say that a plus delta x times I. I being the amount of terms that the number of terms that I'm finding. Okay. So let's estimate the right side sum. Let's estimate Rn. The subscript n being arbitrary amount of strips. Well, remember that this is e to the negative x1. Right. I know what x1 is, and I'll put that in a second on the next line. E to the negative x1 times delta x. Again, I know what delta x is. We'll plug it in a second. Plus e to the negative x2 times delta x plus e to the negative x3 delta x all the way up to e to the negative xn, or xn in this case, delta n, or delta x. Now, let me ask you this. What do you notice in all of these, in this whole sequence? What's common in all of these sums? Delta x. The delta x, the interval is common, right? So can't we remove that out like a common factor? So this right side sum is really equal to delta x times e to the negative x1 plus e to the negative x2 plus e to the negative x3. We kind of did that in our proof that we did yesterday, all the way up to e to the negative xn. And you can do that for any of these sums. That interval is going to be in there for every term, because that's always going to be the base of your rectangle, all the way up till n. So you can remove it and bring it out front if you'd like to. Now, let's figure out what this is going to be. This is Rn is equal to, what is delta n again? 2 over n times, and now this is going to be e to the negative 2 over n plus e to the negative 4 over n plus e to the negative 6 over n, all the way up to e to the negative. Now, what's that going to be up top? If I want xn, what's that going to be? 2n over n, right? 2n over n. Negative 2n over n up in the exponent. which would just be -2, right? I know that's canceled. So let's write this as a sum. Okay, let's write this as a limit of a sum, because that's the goal here. Using right endpoints, find an expression for the area as a limit. Let's not, and we're not evaluating the limit right now. We'll evaluate the limit using integrals, which we'll talk about in the next section. So we say the limit as n goes to infinity of 2 over n times this sum. Times this sum. Now, what is that sum? Well, that sum starts at 1 and goes to n. Right? That sum starts at 1 and goes to n. And what is the function? The function is e to the -2i over n. Because that was the process for finding the exponent. Look at the very end, 2n over n. The reason I didn't reduce that is because I is the amount of terms that I had, right? So it's going to be 2i over n instead of 2n over n within the summation notation. And that's it. That's our answer. Okay. So what I'm going to have you guys do is write the sum using summation notation. You should know what it looks like as a, with a ... in there, as an infinite sum. And what I'd like you to do is use summation notation to write that. The summation notation is going to tie directly into the notation we will use with integrals. Okay. Let's take a look at this problem here. I'll jump into these last two if we get time to it today, but I don't think we're going to. These are just, I wanted to go over examples of homework problems. That's what I was doing here. These are just 2 homework problems that I put in. But I want to talk about this distance problem, because this is area and distance. Let's consider this distance problem. Find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. See, I'm asking you, if I know velocity, can I figure out distance? Right? If I know velocity, can I figure out distance at all times? If I observe velocity, can I figure out distance? Well, distance, again, is velocity times time. If the velocity remains constant, then the distance problem is easy to solve. It's just distance is equal to velocity times time. But what if the velocity is changing? What if I am constantly changing the velocity? That's what I'm looking at here. What if I constantly change the velocity? Well, the velocity is going to be, the distance is going to be velocity times time of each little piece that I know the velocity for. So if I can observe the velocity at a regular time period, right? If I can constantly be observing the velocity, then what I can do is take little snapshots and find the distance at each little piece of that velocity and know what the total distance is going to be. See, what I'm doing here is saying, okay, if I know time, and I'm taking regular intervals of time, and at those regular intervals of time, I'm saying, okay, so say, for instance, I'm speeding up, and I'm taking those measurements of velocity. So velocity here, velocity here, velocity here, velocity here, velocity here. Maybe I slowed down a little bit, right? And I'm taking regular intervals. I'm observing the velocity at any given even interval of time. What I can do is evaluate the distance here, which is basically a rectangle, distance times time, length times width. I can observe here the same way. I can observe here the same way. I can observe here the same way. And I can observe here the same way. And that total sum is going to get me my total distance. So it's kind of like doing the exact same process that we were doing with these rectangles. How did I calculate the rectangle? Again, that was just the time, the length of my interval, which should always be constant, times my velocity, which was my y value, right? Because distance is equal to velocity times time. So what I'm really doing there is I'm really calculating it like a rectangle. Time times velocity, time times velocity, time, and the area that I have underneath the curve is the distance. So what we're connecting here is area, the antiderivative, because we know position is the antiderivative of velocity, right? I'm connecting the antiderivative to area underneath the curve, because that's truly what that is. Total area underneath the curve is actually the total distance traveled. Now, let's take a look at an example of this. So, suppose the odometer on your car is broken, and we want to estimate the distance traveled. Odometer is distance traveled. That's like when you reach 100,000 miles and you click over. Suppose the odometer on your car is broken, and we want to estimate the distance driven over a 30-second time interval. We take the speedometer readings every 5 seconds and record them. Okay. I don't even know why they give you the first part there. I know why, because the speedometer is reading in miles per hour. So what they did is they just transferred miles per hour into feet per second. But what I have here is different readings at 5-second intervals. 1, 2, 3, 4, 5. Check it again. 2, 3, 4, 5. Then they check it again. 2, and they read that for 30 seconds. Okay, constant intervals throughout. What we're doing here is we're actually going to find that the distance traveled is the sum of all of these little snapshots of the distance traveled, right? So what I'm going to do is I'm going to find the distance traveled here. Ooh. I'm going to find the distance traveled here, going to find it here, going to find it here, 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 and I'm going to add it together, okay? Basically what we're doing is we're finding the sum of all of those things added together. Now, what I'm going to actually perform here is I'm going to perform the left side sum and then the right side sum, because I know it's got to be somewhere in between there. I showed it here as what kind of sum? Midpoint sum. Do I know necessarily that midpoint is a good answer? No, we talked about that from the very beginning. We're not sure. It always depends on what type of function. And this is not a regular function if I'm just measuring speed. So what I'm going to do is I'm going to find an upper boundary and I'm going to find a lower boundary for it. I'm going to find an upper boundary and a lower boundary. And then I know it's somewhere in between those two things. So let's find the lower boundary. Let's find the L sum. Now to do so, I am going to find, think back to here. I'm going to find the change in x, the interval, times the sum. So what I have here is I'm going to find the change in x. What's my time interval? 5. In other words, b minus a over n, right? b minus a over n, 30 minus 0 over 6 times it was taken. 1, 2, 3, 4, 5, 6, if I disregard 0, right? So I have 6 intervals that I'm taking it at, okay? You could call this L6. That's what the book calls it. 5 times, and now I'm going to go left side. I'm going to make this on the left side, which means that I am going to include this first number, 25, 31, 35, 43, 47, 45, but I am not going to include the 41. Okay? I'm going to choose 6 intervals that are going to be on the low side. My 6 intervals that are going to be on the low side are these 6. 1, 2, 3, 4, 5, 6. This is going to give me my low side. Then I'm going to calculate my right side, my upper boundary. And I'm going to do that the exact same way. That's a 6. I'm going to do that the exact same way, but now I'm choosing 5 times all of my upper boundaries. Here, 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 here. Starting at 31, 35, 43, 47, 45, 41. Okay. Let's run these numbers. So it's 5 times 25 plus 31 plus 35 plus 43 plus 47 plus 45, which is 1130. I'm going to do that exact same thing. 31 times, 5 times 31 plus 35 plus 43 plus 47 plus 45 plus 41. 1210. So I know the true distance traveled is somewhere between those two things. I know it's somewhere between the true distance is somewhere between 1210 and 1130. Okay. I found my lower boundary. I found my upper boundary. And remember, the L, the left side boundary, is basically taking all of these rectangles starting on the left side of the function. And on the right side is taking all the right side of the function. Basically, my left side is my lower, my right side is my upper in these cases. Okay? My left side does not include my last interval. My right side does not include my first interval. Why the heck does it do that? Every time. Every time. All right. I may start tomorrow's class going over a few examples from the homework. Okay. All right.